Alrighty, good afternoon, good morning, or good evening. So this particular lab or assignment that I'm going to be going over, I'm not going to be going over the entirety of it, mainly for the fact that, the lab itself is kind of the, not necessarily doing it, rather, it's more like, doing math questions and things like that. So for this particular lab, which is lab 7, is going to be going over calculating IPv4 subnetting addresses. So we can kind of look at this as an example. What we're given is we're given a random host IP address. We're given what its original subnet mask would have been, and then we're given what its current subnet mask is. And from that, we need to deduct how many bits of the address are we dealing with that are for this subnet, how many subnets were created, how many hosts per subnet was created, the number of hosts per subnet that was created, the network address of this subnet, the first host of the subnet, the last host, and the broadcast of the subnet. Now, in order to do this, there's some lead ups to this question. Obviously, you need to understand subnetting to some degree, and in order to do that and to make this lab easier in the grand scheme of things, I think it's important that we discuss subnetting as a whole or as a general aspect for those of you who don't know. So what I'm going to do is I'm going to pull this off camera. And first off, we're going to discuss, the IP address or the address as a whole. So let me figure out where my mouse went. Okay. So when we look at addressing as a whole, what we end up having is we have a random number. So probably one of the more common random numbers you're going to come across, let me just change this to a black pen, would be 192.168, probably .1, and then some other random number. So for the sake of this, we'll say .1 probably would be most likely a lot of times your default gateway. This octet would possibly change, and then this one would change based on the host or the device that you're trying to access. So that's a very standard IP address we'd be dealing with. If we broke this down, what would end up happening is we basically have this looking in binary. We would have 8 bits, so 2 to the 8, 2 to the 8, 2 to the 8, 2 to the 8. And if we do a little calculation on our calculators, we can actually say 2 to the 8, and just to make sure that I'm keying everything in correctly. Jeez, I keep losing my mouse. It's a terrible problem to have. Oh, there it is. I guess it's because I sat my stylus on my pad. That's where the problem happened. So set that off to the side. 2 to the 8. Yeah, perfect. So basically our binary, we can represent it as 2 to the 8. So each one of these gets broken down into 3, 4, 1, 2, 3, 4. Gets broken up into 8 bits. So each one of these octets, when you're referring to it, octet 1, 2, 3, or 4, will sort of determine what style of addressing it is. So typically when we're dealing with, some things, if you see something like a /24, that's the default class for a class C address, /16, or a /8 would be the other alternative. All that means is what part of the IP address is the network and what part of that is the host portion. So when we look at this, we have a default classful subnet of a class C. We have a default of a B and a default of a A. So if we look at this in different colors, as I close my color puck, let's redo that. So if we were looking at a we're looking at a C, so the C portion, that portion of the address would be part of the host. If we were looking at a B, this part of the address would be the host portion. And if we were looking at something else, like an A, we would be looking at that part of the address being the host portion. So pretty much all it defines is how many bits are we using for our network portion, and then the remainder will be used for the host portion. So when we look at this, the /8 just basically means the first 8 bits, /16 the first 16 bits, and /24 the first 24 bits. So 8, then we have 16, 24, and then obviously you can't take them all away because we got to leave parts for the host portion. So we have that. So when we're looking at calculating addresses or the available number of hosts or subnets for us, one thing that you got to remember is that there's actually little formulas that we can use for this, for basically the available number of hosts or subnets. So when we're calculating subnets, we can just simply use the equation 2 to the n, where n represents, when we do class lists, represents the number of subnets that are available to us. Or really in this case, we could technically have the number that's here, but we'd have to make sure that we subtract our private address range, as well as the other non-addressable points. Like for instance, you can't have a 127, or you can't have the 10 network as an example. But when we're calculating subnets, we use the equation 2 to the n when we're borrowing bits and we're dealing with class list subnetting. When we want to look at host, we actually deal with a slightly different equation, which is 2 to the n minus 2. And the reason why we're looking at that specific equation, you'll notice it's exactly the same thing, right? 2 to the n, but we have this extra little bit right here, this minus 2 that's happening. And the reason why that's happening is there's 2 addresses in each network that we can't actually use. So we can't use the first one. So the first address, which is all zeros for that host portion, and we can't use the last address. Which is all ones. So the first address is the network address, and the last address is the broadcast. So that's kind of what we have, that 2 to the n minus 2. Now, when we start to break into this whole subnetting bit, one of the other things that I always like to sort of note down, it's a good idea to try to remember that we have these 2 equations here, the fact that we have the 2 to the n for subnets, and the fact that we have the 2 to the n minus 2 for our hosts. But one other chart I like to always note down is kind of when we break down that IP address. So if we're dealing with a class C address as an example, so if we have our address, I'm going to copy down again, 192.168.1, and we'll just pick a random host on that network, say 50. And we said that this was a /24. So we're representing that basically the last octet, that being this one right here, is going to be all part of the host portion, and the rest of it's going to be all part of the network portion, because we know that it's in increments of 8, so 8, 16, 24. So this last one's going to be that way. But in the case that if it wasn't a /24, and say for instance it was a /26, now you start to wonder, okay, well, how are we going to calculate that? Because it's borrowing 2 bits from this last portion. And one way we can actually deal with this is we can sort of break this out. And the way we can do that is, so if I put my dot there, and if we write this binary bit out, so, well, what's the first, let me go from the other direction. So the first binary, if we had a binary as the first bit, that would be a 1. The next bit would be a 2. And actually, even before I do this, let me make a little chart to put this into. Okay. Perfect. And then we can split that place up like that. Split it up like that. And let's see, subnets, binary. And we're going to have one extra, a little bit smaller, but we can make do with it. So what we're actually going to do first is we're going to break this into 8 chunks. So we got 1 chunk there, 2 chunk, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Okay, so if we look at the first part of, and we can kind of imagine like there's an invisible period here. So pretty much we're examining this last portion. So if we broke this into binary, our first bit would be a 1, our second bit would be a 2, our next bit in binary would be a 4, and then an 8, a 16, 32, 64, and 128. And if we look at the next thing, we can, so this is our binary. And if we want to deal with our hosts, our usable hosts as an example. Well, if we remember, our equation is 2 to the n minus 2. So I'm going to write over here on this side, usable hosts. And the reason I write it on this side is because usable hosts, we actually have to start calculating. We're going to be going from the right-hand side. When we deal with subnets that are being borrowed, we're going to be moving from the left-hand side. So from the right-hand side, usable hosts. From the left-hand side, usable subnets, or subnets in general. So if we remember this equation, 2 to the n minus 2. So what does that tell us? Well, it tells us off the bat that, you know, we really can't make a network out of just one. So in usable, there's nothing. Let me get a different color besides black. There we go. N A, perfect. And then when we go here, well, if we have a binary of 2, well, what's 2 to the n minus 2? Well, we can break out our calculator, right, for that if you're uncertain, if you want to do some calculations yourself that way. So we have our calculator here. 2 to the 2 is 4, minus 2 is 2. So pretty much that's the smallest number that we can actually have. So we can go ahead and we can write our 2 here, right? And then we do the next one. Well, what's 2 to the 4 minus 2? Well, 2 to the 4 minus 2 is going to be 6. And then after that, we're going to have 14. And then after that, we're going to have 30 and 62 and 126. And then our last one is going to be 254 for our usable. Now, one thing you might have actually already noticed off the bat is the usable host is just 2 less than the binary of the next number, pretty much. So if we're looking at this one here, 4 minus 2 is 2, 8 minus 2 is 6, 16 minus 2 is 14, 32, etc. So you can look at that as sort of like a little cheater sheet to help you build your usable hosts. Now, if we're going from the opposite way, so if we look over here, let me move this little color puck out of the way, and we look at our subnets. Let me this period out of the way too. Now that we already know what that's for. So we write our, oh, there we go. So we got our so our subnets, it's 2 to the n. So if we borrow 1 bit, well, what's 2 to the 1? It's 2. We borrow 2 bits. It's 4, 8, 16, 32, 64, and then you might continue. You might want to continue, but really we can't continue, right? Because we've already discussed that when this is a class C. If we were dealing with a class C, the smallest we can get is borrowing up to 6 bits. We can't borrow a 7th or an 8th, because if we do, then there's nothing we can use with that space, right? Because if we borrow 6, that leaves us the remaining of 2, and the remaining of 2, we can basically get one thing out of it. So these last two are basically not applicable. You can't borrow them in a class C. And then when we look at the subnet mask, well, all we're doing is just adding things together. So if we borrowed 1 bit out of this, then this octet's portion of the subnet mask, let me just switch to a different color. We'll go with nice lime green. See how that looks. Subnet mask, perfect. So we go there, and our first one is going to be 128. And if we add the 128 and 64 together, what do we end up getting? Well, we end up getting 192. Now, one thing you should be really good at is adding these binary parts together, being able to do binary math quickly as possible, and most importantly, obviously correct. Yes, you can break out your calculator, but, if you want to break this down to a smaller thing, think about what's 120 plus 60. Well, 120 plus 60 is 180. And then you add your 4 and your 8, that's 12. You add the two together, you get 192. So just a little quick way to deal with that. So the next one would be 224, 240, 248, and 252. And then obviously, as I mentioned before, in a class C, these last two would be not applicable. If we weren't dealing with a class C, well, then you could just work them out yourself, right? Well, what's 252 plus 2? Would be 254 and then 255. But I'm going to leave those as NA because we're not worrying about them since we're looking at a class C. Okay. So, if you want to look at these things in their CIDR notation, which is used for if we're dealing with classless space, this would be an example of a /25. This would be a /26, /27, /28, /29, and a /30. Is what we're getting out of these. And like I said, the whole point, and actually not really the whole point, but in this example here, the /30, that's going to be the smallest that you're going to be working with. Probably typically you would find on, say, for instance, a serial link, because on a serial link, it's pretty much point to point. So you get the maximum number of subnets, and your usable host is 2. You only need 2 because it's one side and the other side. So let's continue on and move up. Now, as an example, I'm not going to break down the entire chart. Or I guess I can do it to a degree. If we were looking at the next portion of this, that being a class B, let's get to a black color. And this one we're going to have to write a little bit smaller because we got more to work with. So our top portion is going to be our binary. And then we're going to end up, same organization we're going to do again. Usable hosts. Subnet binary. Usable host, subnet mask. And then I gave an extra spot for our CIDR notation. So now we're going to have to break this. And like I said, we're going to have to conserve our space a little bit more, since I got to fit more stuff here. Instead of being 8 boxes, I need to make 16. And these other ones are going to be a little bit more larger of numbers, so we're going to write a little bit smaller. 1, 2, 3, 4, 5, 6. Oh, that's going to be way too small. 7, 8. Make a little space for our decimal. And then we're going to do another 8 boxes in this little tiny space. 1, 2, 3, 4, 5, 6, 7. Yeah, that's going to be really tiny, but we'll try to figure it out when we get there. So when we look at the top portion, as I said before, is going to be our binary. So we got 1, 2, 4, 8, 16, 32, 64, 128. This space, as I said, is the separation, since we're dealing with now a class B, which means that our 1, 2, 3, 4, 5, 6, 7, 8. Perfect. We're dealing with class B, which means now we're using 2 of the octets for our host portion, and we can borrow from that, and then we have the other 2 octets, which are going to be for our network portion. So our starting out point, same thing as well. Now that we're in the second, we start back at the beginning again. 1, 2, 4, 8, 16, 32, it's really bad too, 64, 128. And you might, like I said, be asking, well, why don't we just continue the binary across? Well, because this is the binary portion, so it's an entirely new number, so we start over at 1 again and we continue on. So now when we're looking at usable hosts, the same thing holds true, right? We can't just magically use 1 bit, so that one's still off the table. And we can almost look up a little bit at our previous chart we had here. Well, what was happening? Well, this one here was 2. And then when we got to the... did I make a mistake? 6? No, perfect. 2, 6, 14, 30, 62, 126, 254, and then you're like, hold on a second, now how do I do it? Because it's a whole nother thing. Well, what would come after this? Well, we would move up to the next one, which, if you were looking at the grand scheme of things, would end up being 512? No, 510 it would be, because this one would technically be a 512 afterwards. So we have our 510, and then we have our 1022 and 2046 and 4094 and 8190, 16382, 32766, and 65,534 for our usable. And if you wanted to figure this out, like you could basically continue the binary across. So instead of doing it the way I did it, and stopping and putting it at 1, you could have just continued counting up. So 128, the next one would have then been, 256, 512, 1024, 2048. So very similar to what you would find in, bits and bytes, so to speak, in a computer, since it's 2 to the power. So next up, when we borrow from the left-hand side, remembering what I was talking about, I said subnets always borrow from the left. So if we're moving from the left, you'll notice a very similarity. Same thing here. And instead of the 2, 4, 8, 16, 32 starting in this section over here, we're actually starting over here because we got to get there, right? So 2, 4, 8, 16, 32, 64. And instead of being not available because we can't take it, we can now because we got plenty of space. So 128, 256, 512, 1024. Remember, it's going to literally be the exact same thing that we did for our host that we were borrowing. The only difference is we're not subtracting 2 every time. So if you want to have a cheat sheet, you can do the subnets first and then just do the other one afterwards. Since it's easier to just do the 2 to the power of something and then deal with the subtraction afterwards. 1024 and 2048, and this is going to become interesting. We got 4096 8192 and then 16384. And then same thing as before, we can't take these last 2, so NA, perfect. And then next up, obviously, we have our subnet mask. And the cool thing about this is it's actually the exact same thing. So 128, 192, 224, 240, 248, 252, and then here we actually need those. 254, 255. And then for this last one, we can start this all over again because it's a brand new block of numbers. So it starts off again for the subnet mask bit is 128, 192, 224, 240, 248, and then 252. And the last 2, same thing, not applicable. And then we can do our CIDR notation. Well, if we're borrowing 1, this would actually be a /17, /18, /19, /20, 21, 22, 23, 24. And then when we continue on, it would be the same thing as up there, basically. So /25, /26, 27, 28. I'm not going to have enough space for this. I'm just going to put 29. And last thing is the 30. And like I said, you can't give away all the portions, so that's the part of the reason why we end up where we are at that little crossroad. So next thing, obviously, is we can go back now to that problem that we had, right? So the problem that we were given is we were given a 192, 168, 200, 139, and we need to figure out some stuff about it. And you might ask, why did I go over all this? Well, it's kind of really important to know what and why you're working with something. So let's make this a little bit bigger. There we go. Let's grab that and shift that like that. Cool. So let's grab our colored pen and we're going to write out the address. So the address we were given was, actually, I don't really like that. It's too light. Let's go with a darker one. Yeah, that's better. 192.16.8 dot 200 dot 139. So we're told that we initially start off with a /24. And that makes life really easy, because if you start off with a /24, it basically says that portion is the network, and this portion is our host. However, in a perfect world, we can never have things that easy, right? So it wants us to now switch this over to something different. It says specifically we're looking at a 224. And you might say, well, what does a 224 mean to us? Because if we remember the /24, it just means that 3 octets worth of bits are flagged. So that means we are given a 255.255.255.0. And what we want is we need a /24. So I'm going to write just the last octet, because that's all that's changing. And what do we do? Well, we look up at our nifty-difty chart we just made, and we look at our mask, and our mask here is a 224, so we know we're borrowing 3 bits. So 3 bits being borrowed means that we're going to be switching this over to a /27, which is all fine and dandy. So 224/27, and I guess I can just write this out, 255.255.224/27. So what do we know about a /27? Well, we have a few things, and that's kind of the best way to approach this, especially if you're new at this whole grand scheme of things, is we look at a /27, means we're borrowing 3 bits. So we have 3 bits for our subnet. 3 for our subnet. We have 5 for the host portion. So if we borrow 3 bits, how many subnets do we have available? Well, it's a class C, so we're actually going to have to shift up a little bit. 1, 2, 3. So we borrow 3 bits. We have 8 subnets. Each subnet is going to have a usable amount of 62 addresses. No, it's going to have 30 addresses, sorry, because we're borrowing 3. We don't have that. So we have here, so 30 addresses, and we have 8 subnets. Cool. Subnet bits. Okay. And like I said, we know that we have 8 subnets, and we know we have 30 usable addresses. And you might say, well, how do I know that? Well, we know how many bits we have, which is 5. So same thing as before, we take out our calculator, 2 to the 5 minus 2, we have 30. We know there's 3. 2 to the 3, we got 8. So really easy. We can go ahead and do that kind of math. However, in the grand scheme of things, if you're like, I'd rather see the reason why, well, the reason why is because if we take our binary and we look at it, and we know, like I said, we're borrowing 3 bits. So those 3 bits that we're borrowing is 128, 64, and 32. And then we're left with our host portion, which is 16, 8, 4, 2, and 1. So our network portion on the left and our host portion on the right. If we add these up, that's where we get our 224. And if we count our options, so we have the ability to be all zeros, 0, 1, like that, 1, and then 1, 0, 0, 1, 0, 1, and 1, 1, 1, 2, 3, 4, 5, 6. What am I missing? Oh, I see what I did. skipped over one thing. 110. That looks better. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And then the rest of it's part of our host portion. And kind of the reason why I'm going through this is these numbers are going to represent the first of our network. So if we have all zeros here, and we have, let me put that back to green, and we have all zeros here, then that's going to be our first network, which would be dot zero. Well, if we flip the 32-bit and we enter in all zeros, then we got a 32. And then you just basically keep adding 32, because 32 becomes our magic number, which we're going to increment by. So 32, 64, add 32 to that, 96, etc. And you can keep going until you get to the point where we reach that host address, the .139. Probably not the most efficient way to handle this, especially when you get up to really, really high numbers. If it was like, as an example, a .40, yeah, not a big deal. We can do it that way. You keep adding to the point where you get to the number you want. The other thing we can do is we can just take our last octet. So our last octet is 139. So how do we make a 139? Well, the first bit needs to be flagged, right? 128 fits into 139. Okay, so now we have 139, and we've subtracted our 128 from it. Well, what ends up happening next? Do we have 139? Can we put a 64 in there? Well, we can't, right? So we can put a 0. Can we put a 32 in there? Well, 32 with 128, that's going to push us over the limit. So no. So you basically keep going down the list and you check to see what you can do. And for the sake of time, I'm going to do this the easy way. So we're going to go to our programmer side, and we're going to just type in our decimal of 139. So it's 1 3 zeros, 1 0. Perfect. So 1 3 zeros. We need our 16. We don't need the 8, and then we need the last 2. All right. So next up, we need to deal with our subnet mask. So we've said that we're borrowing 3 bits. So we borrow 1, we borrow 2, we borrow 3. And the rest are all going to be zeros. So what ends up happening next is we perform a little AND portion. So we perform the AND against these 2 binaries. So 1 and a 1 is equal to a 1. A 1 and a 0 is a 0. Basically, if it's not 2 1s, it's a 0. So we go 1, 2, 3, 4, 5, 6, 7, 8. So we get left with really only one flagged bit that tells us what the network portion of this address is. Well, what's the first bit? First bit is 128. So from that, we can now say we know what our address is. So the network for this address 139 is actually going to be 128 because of that one bit we found. So we can now look at our question, and the first thing it says, the number of subnet bits. Well, we know the number of subnet bits is 3. The number of subnets created, well, we know that's going to be 8 because we've already done those calculations up here. The number of hosts bits, well, we know that's going to be 5. And then we know the usable subnets is 30, or sorry, usable hosts per subnet is going to be 30 because we already talked about that, 2 to the n minus 2. We lose 2 addresses, one for the broadcast and one for the network portion. So we have our 139, or 139, and it's basically saying now that our address, the network portion of this is going to be, we're going to copy out those first 3 octets because they don't budge. So 192, 168, 200.128. And then what ends up happening now is you go, okay, well, great, we have the network address. How do we know what the broadcast is? Well, there's a couple different ways you can tackle this. You know, if you did that whole little charting process that I was mentioning before, so if you went and started listing off all the addresses, like you went 32, 64, 96, you add 32 to that is equal to 128, and then you go to the next one because we already got 128, so no, not 140. Who taught me math? If we add 32 to that, that's 5160. So right off the bat now, we can say, well, the last available address that we have available to us is 159. That's one approach we can do. But the other approach that we can look at is we can actually go ahead and we can do that same sort of math process. So if we know that we are borrowing that one bit and that's the only part that changes, so if we write out the network portion, so the network portion is the 100. And let me change my color, and we're going to do the host portion. Two, three, four, 5. So we know that that is equal to 128. If we copy this one down and then we change all of these to 1s, so we got 5 1s in here, what does that become? Well, that becomes our broadcast for this network. And the broadcast for this network, if we add all those up, is basically one address lower than the next available network address. So it's going to be 159. All right. So then we continue on, and it asks us the first available host and the last available host. Well, if we know what all 1s are, so if we know all 1s is, or sorry, all 0s is 128, and we know that all 1s, the last available network is 159, well, the stuff goes in between there. The first available address is the first of that, and the last available is 1 less, which is 158. And if you're looking at that binary equivalent again, it's just simply our, let me put the red back again so it's clear which part is the network. So we got 100, 0, 0, 0. Okay. And we look at our host portion. So for the first one, we have 5 1s. For the first available address, we actually have 4 1s, and the first bit is flipped. For our broadcast, we have 5 1s. And for the 1 less, we have 5 1s, and the last one is decremented, so it's at a 0. So that's all that's happening, is you're just basically going through this all one step at a time, piece by piece by piece, and working your way through it. And if we want to look at something else as an example, so let's get out the workbook. So like I said, I'm not going to go through all the questions of the lab, just because it's all basically the same thing. I think the biggest key point is before you start the question, finding out what class of address you're dealing with in the classful namespace. You can, reference one of these tables. I suggest though writing it out, and then from there you can then work through it. So if we look at a network, let me just find something to work on. Yeah, sure, let's do this one. Perfect. So we're gonna push this problem up as close. Actually, I'll put it off to the side here. Okay, so using the network diagram, create an addressing scheme that uses VLSM, so variable length subnet masks, show the subnet address, and we're given a class C. So some information we can gather off these sorts of things. These are typical problems that you're most likely going to deal with. Something like 192.168.24.0, and it says it's a class C address, so we can sort of deduct from that it's going to be class full. So we're given a /24 to work with. So some things we need to figure out. We need to figure out how many different subnets we need. We also kind of want to think about the grand scheme of things and what we're working with. So first things first, it's always a good idea to count the networks that you need. So we need 2 WAN links, and I would kind of briefly touch base on those when we were talking about addressing. So 2 WAN links is going to mean that we need 2 available IPs, an IP for this side and an IP for this side. Same thing here and the same thing there. Plus, we also have a network here, a network here, a network here, and a network here. So we have 1, 2, 3, 4, 5, 6. We have 6 networks that we need to assign. Kind of obvious we have 6 boxes, but you know, we're never going to always necessarily be that specific or that easy going forward. When we look at these networks, we know they're going to need different networks because each router that you go through, those connections here, this link, are their own different network. Connecting to a router, these switches are actually on separate networks because they're connecting to a router. If we had a switch hanging out between the two and they were both connected to a switch which was connecting to the router, then this would entirely be one network. It's not that way. So we have a network here, a network here, network here, network here. So that's where we get our 6 networks from. So let me just take those ticks off of all of this. So our first network, typically you want to start with the largest of things and then move down from there afterwards. Or, you know, in some cases, maybe you want to network one side and then the other side. That way you can deal with super netting, but not really something that's needed at the moment. So what we would do is we would, if we were doing a super netting, and as an example, pretending that this was our connection to the internet, then what would happen is you would typically want these side of the networks to all be in the same range. So you'd want to add up your 34, your 18, and then this link, and then have that on one section, and then add up all these, and then have that on one section, and then subnet from there. But we're not going to do that. We're just going to perform it. You know, we're going to do all of our hosts, the large subnets first, and then we're going to do the smaller ones second. So writing this out, we need one that supports 95. We need one that supports 34. We need one that supports 18. We need one that supports 12. And then we need our 2 WAN links. So I don't know why I put 4 there, but anyways, 2 and 2. So those are our requirements. So 95, if we're subnetting this down from here, right? You know, we're going to have to basically make this one of the largest blocks. So what we actually have to give, so I'm going to have a give section. Okay, so what we require is we require 95. What we actually have to give, however, is we have to give it 128 hosts because we can't fit it into anything smaller. And then this is going to be a /25 network. We'll deal with the actual addressing part afterwards. This next one is 34. We have to actually give it the next available one, which is 64. So this is going to be a /26. This is 16 or 18. Now there is no 18, right? So the next available thing we have to give is a 32 because we can't give 16. And if you're uncertain, well, we just go back up and check the chart. So we shift up here, we check our chart. If we need 18, yes, we are going to have to give a /28 and provide it with 30 addresses. Nothing we can do there. And see, when I wrote this out, I'm going to... it's actually not going to be that way. I was going to leave it, but it's probably better. So we're actually giving it 126 because, remember, 2 of them aren't actually usable. So we're actually giving this 62. We're actually giving this 30. So this becomes a /27. This one here, we're actually going to be giving it 14, if I recall correctly. Let me just go back up and check. Uh, 14, yeah, usable hosts. So there still is some waste, but it's really all you can do. There's nothing much else that happens. And then these last 2, good thing we can give them both 2s. So these last 2 are going to be /30s, and this one here is going to be a /28. So I think the easiest thing we can do here is let's just make a quick copy of these. So we can drag this down and we can work with it together. Control C. Chuck this here. Make it slightly smaller so it fits in like that. Okay, so if we're subnetting out the first thing, so what ends up happening is the first network starts at 0 and it becomes a /25. What does that mean? Well, the first network is 0 through 120. 128 basically, because the next network starts at 128, so it's actually technically, I guess, 127. So our next network, like I said, starts at 128 since we're borrowing that. So we can go 128. And then this, as I said, needs to be a /26. Well, a /26, our magic number is what? Instead of being 28, it's going to be, or 128, it's going to be 64. So this network runs from 128. We add 64 to this, so 120 plus 60 is 180. We add that is 192. And 191, and our next network starts at 192. And this is going to be a /27, as we said already. What's a /127 counting by? It's counting by 32, right? So something interesting about this specific one, which you may or may not have already noticed, is it's kind of following that whole subnet mask system, right? Because if we look, the subnet mask is a 128. The next subnet mask is going to be a 192. The next one after that is going to be a 220. That was a really bad 4. It's going to be a 224. So what we end up doing is this one now is going to be 192 to 223. And then the next one after that is going to be starting out at 224, and it's a /28. Well, what is a /28 increment by? A /28 increments by the last bit of the network portion. So the last bit now, instead of being 32, is now 16. Right? And if you forget that, we just simply go back up. We can check out our chart we made earlier. So incrementing originally by 128 when it's a slash 25, incrementing by 64 when it's a slash 26, slash 27 increments by 32, slash 28 increments by 16. So our next one, let me just shift that back over so it's back in frame. So that becomes our subnet mask. So this one is 224, 2239. And our next address starts at 240, and it is a slash 30. Well, a slash 30 increments by 4, right? So this one is going to be 240, and it's going to go till 243. Subnet mask for this one is 252. It's not going to be following the same process because these just happen to be in order. Now we're jumping from a slash 28 to a slash 30, so we kind of lose out on that benefit there. The next one in line would be a 244, which is a slash 30, and we would end up with our addresses going from 244 to 247. And the subnet mask with the last octet of slash 252. So when we look back at this, and it asks us for our networks, well, we can sort of draw these in now. So the first one, this one was a 192 dot. It's not going to be very easy to draw in that small space. So I'm just going to draw the last bit. So this one, its network was the second one we did, the slash 26. So it starts at 128, and it's a slash 26. And then we have our 95, which was our first one. It starts out at 0, was a slash 25. And then we have our other network, the 18. That was the third one we did. So that one starts out at 192. Put my decimal in there, 192. That one was a slash 27. We have our 12 hosts. That's a slash 28. So this one here is our next one. So it's a 224. And it is a slash 28. And then for the WANs, you know, like I said, unless you were doing super netting, that would be the only real process that mattered which one got which. But since we are, it doesn't really matter in that case. So our next one is 240, which is a slash 30, and this one is 244, which is also a slash 30. Now, I'll take one of these as an example, and I'll give you the calculation. So remembering what we said before, with the whole addresses, the first one is the network portion, and the last one is the broadcast. So if we take this first address as an example, and we enter in that last bit can't be switched, which is a 0, and then we enter in all zeros for our host portion. 1, 2, 3, 4, 5, 6. We need one more for 7. So obviously we already know it's a 0, but if we set our network a 0 and we set all of the other bits as 1, we go 1, 2, 3, 4, 5, 6, 7. This becomes 127. So this one is our broadcast. And this one is our network. And then the ones in between, so .1 and .126. That would be our usable range. So 1 through 126. Network range for hosts. Now, one other interesting tidbit as well. I don't know if they actually added into this inclusion or not, where it says 34 hosts. We really don't know if it's actually including the interface on the router. And that technically needs to take up one of those addresses. So actually, in the end, we really don't have 1 through 126. Usually it takes the first address or the last address for our default gateway. So we can say then 2 through 126 is actually the number that we get left over. So we don't have 126. We really actually have space for 125 hosts. And you can do the same thing for each thing, right? Like, so when we do, as an example, the WAN links, I'll use one of those because that's probably going to be the more common ones. 240, 241, 242, 243. So same thing. Last one is our broadcast. Oh, that's a really, really bad A. First one is our network. Side A, side B. And what I mean by side A, side B is basically one side of these has to have an address, right? So if you were looking at these, as an example, this one could have 241, and then this one over here could be 242, and on this WAN link, 245, 24, 246. And then if we were looking at this one here could have an IP address of the first one, and this WAN link, this link over here would have 193. That one would be a 1, and this one would be 225. So I know it looks like a spaghetti mess, but if you were following along with me on the way, it shouldn't come as any, surprise that this is, quite important task to know and to have, but also to be able to work through, right? So we saw that problem, we went through it, we broke it all down, what our requirements were, what we actually had to provide based on the rules of, IP addressing, and what sort of mask we were dealing with subnet. And then we just break it out from there. So as I said, we had our /25, 26, 27, 28, 30, 30, and that's kind of where we got our subnet mask, and we were talking about our magic number, so to speak. But yeah, so 128, 192, 224, 240, and then the subnet mask last octet would be the 252. So that's all I have. That brings us in our recording up to, how long were we going for? Oh, actually almost an hour. So I would say that's a pretty solid explanation on the process for this particular lab, and it should get you towards your answer. So thanks for being with me, and thanks for your help. Take care and have a great